As Jörg already introduced in the morning, I'm going to continue the Pyiron part. So that was a major part of my PhD work together with Jörg at the MPIE. And I now moved this also to Los Alamos, doing my postdoc with Danny Paris and looking into materials at extreme environments. And that's generally part of my fascinations with this question of how can we use the upcoming generation of exascale computers to gain new scientific insights, right? And just running larger simulations or running with a more expensive force field, the same simulation as previously is maybe not the most effective way to do so. And so in this context, what we try to do is really predicting material properties directly starting from atomistic structures and ideally having autonomous workflows, right? So where we have no more need for human intervention during the workflow to really be able to iterate over the whole periodic table. And in this context, Pyiron is really the framework to, on the one hand, rapid prototype these workflows, so really accelerate the development, and then finally upscale them to really run on the exascale without rewriting the whole workflow and doing everything again. This is all motivated by the general motivation, I guess, for material science to be able to iterate over the whole periodic table and find the interesting alloying elements. Right? So we heard this example of magnesium before. Magnesium is lightweight. We would like to use it for many engineering applications, but unfortunately already at like 10% compression, it becomes rather brittle, so it's not very useful at the moment. And then if we search the periodic table, we can find combinations. So here in this case, 1 weight percent of aluminium and a tenth of a weight percent of calcium. And with this, we can form a highly ductile alloy while still keeping the lightweight and all the good properties that magnesium offers. Right, so we would really like to find these kind of special combinations in the periodic table in an efficient way. And if we just do a very rough estimate, like a back of an envelope calculation, let's say we have 3-component alloy, that's roughly 5,000 different combinations that we can have. We look at 10 different concentrations, so that would be just concentration steps of 10%, and 20 different temperature steps of 100 Kelvin that already result in 1 million experiments. Right, so you quickly see that this becomes impossible on the experimental side and even for the simulations, right? So doing a million different calculations or in general, 1 million calculations really stretches the capabilities of our existing tools. And so that was really the motivation why the Pyiron project was started, to really be able to handle this huge amount of calculation. And what are the kind of properties we want to calculate? We can start with formation energies and just look at the basic part, but it becomes very interesting once we're able to really compare one-to-one to experiment. Right, so that's what you see here, the heat capacity for calcium over temperature. And we can see this very nice match for the low temperature FCC phase, where the two theoretical predictions for the LDA and GGA functional perfectly agree with the experimental data. And then for the high temperature BCC phase, we find that they agree with the lower branch, but not the upper branch there. And that's very important because previously, the CalFORT database, which is used for many engineering applications on larger scales, relied on this upper branch. And only by showing them these kind of theoretical predictions and show that the theoretical ones agree with the lower branch of experiments, we were able to convince them to update the database and also agree with the lower branch. Right, so we're really now at the stage where we can not only use theory to make qualitative predictions, but really make quantitative predictions that one-to-one align on top of the experiments. Right, so that's with this technique that Jörg really drives in the department of developing Hyperparameter thermodynamics, it's possible to make quantitative prediction of material properties. And how is this done? I will only go very briefly into this. You're happy to ask me for more details afterwards. But in general, it's really like an adiabatic approach. So we add the different contributions to the free energy. We start with our equation of state, and we have the electronic temperature, the phonons, then we would use like finite displacement methods, and finally the thermodynamic integration to get the anharmonic contributions as well. Right, so we could also get all these contributions basically by running a very long DFT molecular dynamics trajectory, but that would be highly inefficient computational-wise. Right? So we really want to find ways how to calculate this efficiently. And so if you look here at the different codes, it's basically the perspective of a PhD student, right? So it's always nice to see the abstract methods. But as a PhD student, I won't implement them all again. I will use existing codes and I have the challenge of combining them. And that's where we have, again, this challenge, different interfaces, different input-output formats, different units, different names for the same variable. All these what we have to figure out to be able to couple these codes and really make a continuous workflow there. Right, so what we would do a thermodynamic integration once, or we would run a very short DFT ab initio a DFT MD trajectory. Then to this trajectory we would fit a machine learning potential only for this specific temperature. And then from this potential, we would first do a thermodynamic integration from the harmonic reference to this potential, and then from this potential to the DFT calculations, right? And that's really the computation most efficient way to be able to calculate this ab initio thermodynamic calculation, really, to calculate this with a high precision. And so the message here is to make it efficient, and we'll be able to run this over a large scale. This typically results in rather complex simulation protocols. And that really makes clear why we need tools like Pyiron to really address this complexity of the simulation protocols and run these kind of protocols really at scale, iterating over the whole periodic table. And when I came to Los Alamos, that's something that's also there when looking into materials at extreme environments. Right? So Danny is really an expert of extending the time scale of molecular dynamics trajectories, which is very useful, pretty much required to understand diffusion, in particular in fusion materials. And also this results in rather complex simulation protocols as illustrated here, right? So in the Exascale framework, to splice the trajectory and connect them all, we run multiple workers, all running individual snapshots of the MD calculations, bring this all together. And so the goal was now during my postdoc to connect these two parts and calculate really barriers with ab initio precision, right? So really trying to bring together the expertise from two different communities. On the one hand, the ab initio thermodynamics, and on the other hand, the materials for extreme environments, or primarily the diffusion properties using long timescale MD to really put barriers and hopefully even a quantitative understanding on the barriers. Good, and I guess as you heard, the second workshop, the tool that we used are definitely the machine learning potentials, right? So for those of you in the long-term program, I will keep this part very short. The general idea of our machine learning potentials is to go from a database of atomistic structures, do some fitting with a rather complex form, and then we have a validation step. And if we now look into the fitting process in a bit more detail, we can usually divide this into two steps. The first step being we map from our atomistic descriptors, from our atomistic structure with like XYZ coordinates into a descriptor space. And these can be simple descriptors like the EM potentials, or more complex ones like the SNAP, the bispectral components, or the ACE potentials that I guess Ralph is going to talk about on Wednesday. And then from this descriptor space, we have a second step where we map from the descriptor space to pair atom energies. And so there again, we have a wide range of options to choose from. We can start simple with like a linear regression model, or like a Gaussian process, or even up to a neural network. And it's still an open question of like, how much complexity do I need on the descriptor side versus how much complexity do I need on the model side, mapping the descriptor to the pure atom energies. And so we collaborated there with Andrew, who I guess many of you also know, as he's a participant of the long-term workshop on the FitSnap package, because the FitSnap package really, combination with LAMS, allows us to build arbitrary combinations, right? So we're no longer forced to have one descriptor with one model, which is typically produced as like one machine learning potential, but we now really have the option to build arbitrary combinations, try different descriptors, to try different models to map from the descriptor space to pair atom energies, and really have the combination there. And what was my contribution there was primarily to understand this coupling. We wanted to have it available as like a Python library, so it can be directly integrated and really do this kind of high throughput studies over the parameter range there. So the challenge, if we look again at our materials for extreme environments, is on the one hand, we want to be transferable, right? So we really have to cover structures far away from the equilibrium, while many existing potentials are typically more fitted around the equilibrium. On the other hand, we have to be computationally efficient, right? So really running long time scale molecular dynamics trajectories and be stable for this time, and also spend as less compute time as possible on this, and still being precise. So let me focus on the last two parts first. All right, so here you should see this benchmark study, which was, I guess, referenced quite a lot in literature. You see there are some potentials here illustrated by the gap potentials, which are very precise, but unfortunately also very costly. Those are maybe not so useful for doing long time scale MD simulation. And there are other potentials, like here illustrated for the moment tensor potentials, which are only slightly worse in terms of the optimal precision that they can reach, but nearly 2 orders of magnitude more efficient. So those obviously make a lot more sense to run long time scale simulations. For the remainder of this talk, I will focus on the SNAP potentials, ones in the linear way, which are a bit more away from the Pareto frontier, and the quadratic snap that you see here as green symbols, which are much closer. Yes. And now coming back to the third part, right? Basically, how can we build transferable potentials, right? So how can we make sure that we really cover the whole space of our configurations or the phase space, basically. And there we basically inverted the process. So to generate very diverse configurations, we increased the informational entropy of our descriptor and used this to maximize the diversity of our configurations. So that's what you see here. So using the entropy method, we achieve a very bright coverage over the descriptor space, just illustrated by 3 descriptors here, in comparison to, like, for example, an expert set, which is illustrated in purple here. And by having this method to really drive the information entropy, what we typically get are rather diverse structures or liquid-like structures. There are some atoms in there which look like the atoms that you see from ground state phases, but because there are commonly roughly 50 atoms in a cell, many other atoms in the cell are rather diverse and really span a whole range of the descriptor space, resulting also in a wide range of spread in terms of our configurational energy per atom. So really by maximizing the information entropy of our descriptors, we really achieve a very diverse set that we can then use to fit our potentials to. And if you do so, we find that it's much harder to fit to this set compared to many of the expert sets. Right, so we see here for a range of potentials, all using the snap descriptors as an input, a couple of neural network-based parts and linear and quadratic snap. We see they all on the domain expertise set achieve a precision of around 1 millieV. Right, so we really see like how the quadratic snap goes down here, everything is fine. While in contrast to this, for the information and entropy maximized set, they really seem to saturate at something like 10 millieV. And this is consistent really over all the different types of potentials, which made us ask the question, okay, what is really happening there, right? So why are the best models not able or only able to converge to 10 millieV, and why we are not able to go down to, for example, 1 millieV? So the first part we looked at was what is the impact of our DFT precision, right? So the uncertainty of the DFT data that we train our potential to. So here we pick 2 elements. We took tungsten and beryllium because those are very relevant for the fusion reactors. And then we looked at different levels of DFT precision, right? So we increased or decreased our K-point spacing and increased our energy cutoff, just to get a reference, okay, how precise do we need to be? And we see for beryllium, basically going from the solid lines, that's our lowest level convergence, to the medium, we see a shift. But then going from medium to high convergence, there's basically no more difference in terms of the fit, and it really lies perfectly on top of each other. In contrast to this, on tungsten, we see really there are 3 discrete lines that the different set of parameters really result in different fitting curves, which relate to different potential energy surfaces. And then there were a lot of discussions, okay, tungsten having more electrons inside the pseudopotential, so it has to be more complex, and how this complexity influences the challenge of fitting this. But what we realized, maybe more by accident, was if we look at the distribution of our configuration energy per atom, and we compare this for tungsten and beryllium, we see that the distribution for beryllium is much more narrow than the one for tungsten. If we now take the distribution from beryllium, if we just rescale it to roughly by eye match the one from tungsten, that's what you see here in green, then suddenly fitting tungsten is as difficult as fitting beryllium is as difficult as fitting tungsten, right? So that's where the important part here for everybody who's fitting potentials, it really depends on how much of configurational energy you're covering. And so maybe just reporting RMSE values in this community and just saying, okay, I achieve an RMSE of 1 millieV is maybe not the full message. It also depends on what was your test set. Did you have a very narrow distribution? Then it's very easy to get an RMSE of 1 millieV. If you have a much wider distribution, then it's more challenging and it's much more impressive for your potential to really achieve this. All right, so that's what I try to bring as a first learning for all the people using machine learning potentials. The width of your per atom distribution is just really like a good indicator what to look for there. And then together with our summer student Jason Gibson, we looked into the other hyperparameters, right? And this is really what Pyiron enables us here is really to do this kind of wide scans through all the parameter ranges. Previously, we scanned over the different DFT parameters. Now we are able to scan over the cutoff of our potential, as well as the number of parameters inside the potential. And the first thing that we find here is really how the optimal cutoff radius is changing. Right? So for a long time, the cutoff was really set like a given parameter defined more or less on the radial distribution function based on the equilibrium structure. Right? So people typically said, okay, I want to include like the second nearest neighbors or the third nearest neighbors, and that's how they specified the cutoff. What we find here is really that the cutoff is more or less directly correlated to your, the optimal cutoff is really directly correlated to the number of parameters you have. If you have a more flexible potential, you can benefit from having a larger cutoff and basically gaining more information from the surrounding neighbors. If you have a less flexible potential, it makes sense to go to a smaller cutoff, and because you're anyway not able to capture this information. Right, so it's really what we feel here is that with tools like Pyiron, helps us to identify where there was like a human bias, right? So we always say, okay, we're physically motivated, we know how the cutoff should be defined, it should be just the second or third nearest neighbors that is our motivation, and now doing this kind of parameter studies, we really find it's much more of like a less physical, but more like a numerical parameter, the cutoff and how to optimize it. Talking about this parameter study, we also looked at the computational cost, right? So how does the computational cost of our potential change if we change our parameter or our cutoff radius? Right, so that's what you see here in terms of two different graphs. So one's in the nanoseconds per day and the hours per nanosecond. And where in the beginning we really see like a huge dependence on the cutoff radius, while if you go to higher number of parameters, the dependence on the cutoff radius becomes from smaller. Right, so that's what was a bit surprising for us in the beginning, but basically what this means is it's not always the best choice to go to the smallest cutoff radius, but if you can reduce the number of parameters by going to a slightly larger cutoff, this can really be beneficial. And so the main dependence there is really much more on the number of parameters that we have. And so that's what I did here. So on these curves now, the color of our lines represents the computational cost at this point. So if we take one line and we follow it from right to left, we basically see that the color becomes darker as the computation cost gets cheaper. And this helps us to identify a new optimized Pareto front. And this time, what is the cheapest potential to achieve a given level of precision? Which is really the kind of quantity that we are interested in doing these kind of long timescale simulations and optimizing for this. So we can again plot this in terms of like our RMSE and computational time. And you can say, okay, that's a nice study. It's nice to know this result, but what does it really affect us on practice? What are like the challenges that we have with this? And when we compare this to the previously used potential, we're like in factor 8 faster than what's previously there, right? So really by doing this parameter study, running once this complex workflow, using a tool like Pyiron, we're really able to get a factor of 8 speed up in our calculations, just by having an optimized potential to achieve the same level of precision. Right, so the second message here is really that the cutoff radius is much more of like a numerical hyperparameter and much less dependent on something like the radial distribution function. Obviously, it changes for the different elements, and the radial distribution function gives you a good first guess. We really recommend to do these kind of parameter studies to identify the optimal cutoff radius, in particular when you're interested in running long timescale simulation. Now coming back to our challenge, right? So we wanted to go below 10 millieV for this potential. So we now applied the same studies for different types of potentials. Right? So we started with a quadratic snap. And what you see here, we finally were able to break the 10 millieV barrier. Right? So we got down to 9.8, but that was not so much as we expected. Right? So we see this here in comparison. So we were at 10.9, now we are able to go to 9.8. But the important part here is that we use a much smaller number of bispectral components because we just have the quadratic terms. Right? And that's, if you look here again at the RMSE over computational time, we see if you're fine with a rather large RMSE error, then it's better to choose the linear potential. But then already at a certain point, you really see this kind of transition where it's much more effective to use the quadratic potential, where you can gain nearly an order of magnitude in performance improvements using quadratic descriptors versus linear descriptors for the most precise potential there. And so it's really, for high precision calculation, the quadratic snap descriptors are an order of magnitude more efficient than the linear ones. And then we included the forces in our fits. So all the previous plots were only fitted to energies. Now we also fit to forces. And for the first time, what you see now is really whenever we increase our number of parameters, we systematically also improve our fit, right? So it's much more stable, much less noisy than compared to the data that we had before. Unfortunately, the issue with this kind of including the forces is really the huge amount of memory usage. Yes?
So what are the units on y-axis? Should be electron volts per atom, per angstrom, or what?
Sorry, I only show the error reporting on the forces. On the energy, sorry. Just to be consistent with the previous plots, right? So on these plots, I always just fit it on energy. So also now for the force comparison, I just show the energy error. But I include the force in the fit, basically by weighting them 1 divided by 150, which is basically to have the same weight between energy and forces.
So, and another question is JMAX 21 versus JMAX 2J8. I thought that you increased to JMAX, you increase the number of parameters, and you're showing different trends, right?
Yes. So you mean if I push this even further?
No, what I'm saying, 8 should be contain less number of parameters compared to 21. And it's...
Yes, but you have quadratic terms, right? So that's why I report both values. If we take the quadratic terms of our bispectral components, we still have the computational cost of just calculating them. Like, we only calculate up to J2 max equal 8. And then we do the quadratic parts of those descriptors, but that is basically no computational cost. Right, so that's why I report the J2 max to have like a comparison between the linear and the quadratic. Yeah, so it's possible now to go to much lower errors, but the issue is there really the increase in the memory, because we have to, per atom, have the derivatives of our descriptors, so it's really increasing quite drastically, in particular for this set where we have like 20,000 structures and roughly 50 atoms per cell. And there was a point where, again, we got stuck, right? So we're now finally able to get there, but it's very costly, it's not so much fun. And then we figured out, okay, we can combine multiple cutoff radii. Right? So we just said, okay, the idea was to have like a radial derivative of our descriptor in there, of the snap descriptor, and really see how this affects the results. And so we took 2 samples, one always covering the whole range, so going from 3 angstrom to 9 angstrom and increasing the sampling density in between. And the second one starting around 4.6 angstrom and really increasing the sampling around this point and really just extending it. And what we find is really that we're now able to go to 7.1 milliV on the same data set, right? So we really can improve this, and this is basically just by a very small increase, right? So we still use a linear model and just fit to energies here. And that's great. We were happy for a moment. Then we realized, okay, let's do it just a self-test, right? So just get a feeling how dependent the snap potentials are on the specific cutoff that we choose on this data set. We said we take one potential at a 4 angstrom cutoff, and with a maximum number of parameters, just a linear potential, and then we fit the other potentials to this potential. And we expected that if we go for larger cutoffs, there should be just a small increase in the error, or maybe even like more or less stay constant there. But what we find is that the snap descriptors are very sensitive to the error, to the cutoff radius that we choose. Right? So that's what you see here. Already, if we stay at the 4 angstrom cutoff and we slightly increase the parameters, we only get a little bit worse. But if we just change our cutoff radius, just go slightly larger in terms of our cutoff, that's really where the error directly jumps up above the 7.5 millieV. And from this, basically what we concluded is now that the snap descriptors are insufficient to study this materials at this extreme environments. And I look forward to the talk from Ralph Draughts to really learn more about the ACE descriptors, and maybe they can help us here to understand this and include the radial dependence. Or we would be interested to do the same test there to see if they show the same effect there. So what does it mean? What's the current state or where we are now? Right, so in the end, we really want to understand the transition barriers and how the uncertainty is affected there. Right, so I just show this here in terms of a carbon atom transitioning from the octahedral side to the tetrahedral side and then to another octahedral side. And we really want to put an uncertainty on this barrier and see how the barrier could shift within this uncertainty. So we'll be able to make quantitative predictions on the long time scale calculations and for diffusion properties. And I hope I was now able to give you like a first introduction, like how we use Pyiron to get this kind of data and where we need this kind of very specific parameter studies to be able to understand how the parameters are related and how to optimize these parameters. And so for the next couple of minutes, I would give you a more broader or more technical introduction in Pyiron and how we achieve these results, or what are the methods that we use there. But if there are any questions, we can also maybe have questions on the first part now, and then I would jump into the more technical part. Yes?
So I understand that you have your atomic configuration, map it onto descriptors, get your energies and forces. Is there a way to go back? Like, I want to have a certain atomic configuration, and I know what the energies, what energies and forces I want to have. Is there a way to come back around?
So in a certain way, that's what we try to do with the entropy maximization, right? So there we say we want very diverse descriptors, so we can, like, from our descriptors, we can generate artificial forces to drive our configurations. So that could be an option, but the question is, like, what are the configurations that we would end up if we say, okay, we want this specific energy. If it's a high energy, okay, I guess it's easy to find those. If it's a very low energy, it might be harder to find those specific configurations with this kind of technique. Good. Then I jump into the next part. So now I really want to go into the technical details of Pyiron and show more how this is connected. And as Jörg already introduced, right, so with Pyiron, we very heavily rely on the Jupyter notebooks. So really trying to make this transition from the terminal that we all used for many people use for decades. We want to now switch to a more modern interface, here represented by the Jupyter notebooks. And this has a couple of advantages, right? So we can really start first by seeing our structure directly in the Jupyter notebook. And that's very helpful to, for example, identify if there's overlapping atoms, which would directly cause our calculations to crash. And we don't have statistics like how much time this saved, but we know from previous experience that many people submitted calculations, there were some overlapping atoms, they were boring angstrom, not converted correctly, and these calculations just run forever and give very cryptic error messages, and then you increase the CPU resource and so on, right? So, like, it's very helpful to just look at the structure before you submit your calculation to get a first feeling there. In addition, we have the ability to add markdown text inside our Jupyter notebook. So to really cover the whole process of, like, what is my idea? What is the kind of calculation I want to do? What is my expected outcome? Maybe write this down before you submit the calculation to really see, okay, was my hypothesis correct? Can I maybe get a more efficient way, or where maybe I made a mistake? And then also really cover the whole process, right? So from creating the calculation, submitting the calculation, and then analyzing the results. And we'll go into this in more detail on the following slides. This started all at the Max-Planck-Institut für Eisenforschung, right? So that was, or even before my PhD, but then during my PhD, we really got it to a stable level and really drastically increased the user base. And then from there, it first started to reach more groups in Germany. So the group from Ralph Drautz at IPAM, the materials modeling group from Carsten Albe, and then also internationally, like Skoltech, the University of British Columbia, the Center for Molecular Modeling in Belgium. That was also the group that first used Pyiron in terms of like a lecture series and really implementing a whole new set of codes. And they said for students coming in, right, so if they just start with their program, you no longer have to teach them how to use VI, you no longer have to teach them how to navigate on the file system. This Jupyter interface, that's already more familiar to them. Right, so they might have done a machine learning tutorial somewhere, and so they feel home there already. And I guess it's really required for our community to also embrace these tools more, because if we still say, okay, you have to learn how to navigate on the file system, on the shell, and use VI to edit all your files, there's really a barrier for new people to enter this field and join there. And on the other hand, having the Jupyter interface, we can also couple more easily to machine learning people, or maybe also make it more attractive for mathematicians to say, okay, now I can run my own simulation and work with the results rather than I have to collaborate with somebody to run the simulation for me to then build a model on top of this. And so the idea here for Pyiron is to abstract the technical complexity so that we as scientists can focus on the scientific complexity. In terms of an abstract model, we try to visualize this with what we call the simulation lifecycle. So here this idea of you have a model in mind, you define your project, and the project would be the specific calculations you want to do to validate or falsify your hypothesis. And you would define this in terms of a generic input, and for Pyiron, this would be the Python programming language. And then everything in the gray box is really where the the framework takes over, and this is really fully automated there. So the framework takes the generic input and translates it to the code-specific input. So the important part here is, with Pyiron, we don't want to re-implement all the methods. We really see it more as like very thin wrappers around the existing simulation codes or existing packages developed in the community. What this wrapper is doing is really just translating the units, because many different codes have different units, or maybe the variable names are different between different codes, and so on, right? So like, to have really this connection from a generic format to the code input, then we can run our simulations. I will show this in more detail. Then generally you can run it on your laptop, or you can also submit it to a HPC cluster. And finally, when the calculation is done, you get your output, and again we transpose this output in terms of to a generic output. And by having both the generic input and the generic output, we can really separate the analysis part from the submission part. So you no longer have one analysis working with one simulation code, but you really can apply any kind of analysis to any kind of simulation code. You have much more flexibility there by relying on a generic format. And so for somebody who's now maybe developing a new DFT code or a large-scale DFT code, if they plug in here, they directly have access to all the analysis methods that were already implemented in Pyiron, right? So really having access to a much more larger range of tools and options there to analyze the results of their code or couple their code to other tools. So this job validation, for example, could be looking at the electronic convergence of our DFT code. We can also collect the data. Maybe we have multiple calculations, finally do some analysis, maybe a fitting of our results, and then visualize the results for the user. And that's where the user takes over and says, okay, is this consistent with my model or my understanding? Or maybe do I have to do another iteration of this loop and redefine what kind of calculations, maybe do some more calculations to get a further understanding there. As Pyiron is really covering this whole simulation lifecycle, we also maintain the provenance of the workflow. Right? So if you do all this in an automated way, you can take the notebook, maybe give it to a summer student that's coming in, and he can basically more or less directly continue where you left off. There's no longer this kind of knowledge loss, or there's so much training required to get a student to start at the same place again. Internally, this is achieved by what we call the Pyiron objects, or you can imagine them like building blocks. And if you spend a lot of time on playing with Lego, so I always say building blocks are just like Lego. You put them together to really get simulation protocols, right? So all that we do is basically just define the standard interface, and then you can build arbitrary complex simulation protocols. Each Pyiron object is on the one hand connected to resources. So those can be our specialized simulation codes, LAMS, VASP. It's connected to the computing cluster so that we can submit it to the cluster, and parameter databases. For example, the interatomic potentials from the NIST database, or also experimental parameters that we might use as a reference here. It's also connected to a data storage. So there we use the hierarchical data format, in particular to be able to really store the long MD trajectories in a very efficient way. Right? So that's where we saw that other formats like JSON, which is commonly used in kind of these high throughput studies, really came to their limits. And the HDF5 format in combination with like an SQL table to track where the objects are located will allow us to store trajectories more efficiently. And finally, these objects can be serialized. With this, we basically mean if the calculation might not work as you expected, it might crash on a compute node. It can save all its current memory state inside the HDF5 file, and then you can reload it on your login node. I mean, we identify, okay, at which step did it break down, where maybe the issues, and really understand, okay, what went wrong there. Finally, for the user, we use the Python programming language and use some kind of operator overloading and factoring. I will show more about the user interface on the following slides. And so the Pyiron class, the general part is really just they are building blocks to construct complex simulation protocols. So now jumping into it, for the following slides, I will really try to show a bit of code, and it's also, you can try this out. So if you go to pyiron.org, as it's listed here, we have a MyBinder environment where we can really play around with this code and reproduce the examples that I show here, or at least some of the examples. So the first part is we create the project. So rather than other systems where maybe the database is something very abstract, what we try to do is really have the database related to the folder structure that we are all used to. Right, so when I create a project, it really creates a folder in the background, and all the calculations that are executed in this project are also represented in this folder, right? So you find the output files, you find the underlying data in this folder, you can access it. move the data around, right? It keeps the same structure. And we communicate this information by the factoring pattern. So that's what you see here. We use a project to create our LAMS calculation object. So the LAMS calculation object already knows that it should save its data into the folder of this project. Right? By just having the project here as an object which creates the LAMS object. The same applies to the structure. Jörg already showed how we can access databases like listing the potentials. Here just select one, and then I select the number of cores. And finally, when I call the run command, that's basically when I go through the whole simulation lifecycle and do all the automation part. Right? So I don't have to specify where to save the data. That's already communicated by the way how I create the calculation. I don't have to specify where my executable is located. All this is only configured basically once, and then reused in every simulation protocol. Right? So the goal here is really that what we have in the Jupyter notebook should be as close to the scientific steps we want to do as possible, and have as little as possible technical information that are specific maybe to one supercomputer. So you should be able to take one simulation protocol and bring it from one computer to another computer, or even share it with collaborating partners who have access to different resources. So really the resources, as I said, right, so executables, interpreting potentials, queuing systems, they are all configured once for the Pyiron installation, and then they are reused in every simulation protocol to really make this transferability of simulation protocols much more easy. In a second. Good. Now we can make a bit more complex simulation protocols. Here I calculate an energy volume curve as I started with in the motivation, right? And I guess we had this question previously of if people use these kind of black box tools, do they lose all the physics understanding, right? So if they're just pushing a button, how much do they still learn? So what I want to highlight here is really we try to maintain the physics in the Jupyter notebook and only try to automate the part that's on the technical side. So really running a lot of calculations. How much should the student have to learn about how a queuing system interacts, or all these kind of technical skills, which maybe we say, okay, for a physics degree or for a material science degree, or even a math degree, it's not so important how to know all the VI commands and all this, but it's more important to know the physics or the math of the underlying problem. Right, so here, just showing it for the volume strain, you would still do the change of your strain to adjust it to the structure, but really have the physical steps, right? So I have my strains going from minus 10% to plus 10%. I copy my structure, I apply the strain there, and then here I use the VASP code. So that's unfortunately not available in the virtual test environment because VASP is a licensed code, but in general, you can also use other codes and then run my simulations. And you see basically it's a for loop, so it's creating a couple of calculations and submitting all of them. And now the first part where this kind of technique of Pyiron comes in, if we now want to access our data. I previously said, right, so we have the project, which is a folder on the file system. We then really have like a semantic path that already starting from the project, you can navigate through the whole data structure. Right, so that's what you see here. So I created my calculation, that is here calc 0 as you saw. Then I go into the output, the generic part, so that's the part that's independent of the specific simulation code, and get the total energy as well as the volume. So maybe I want to plot like an energy volume curve. The important part here is I don't have to load the job before, but the HDF5 file is really like an extension of our file system, and we can just use the same slash-like notation as we know it from folders on the file system. Right? So it's really just, the way we think about it is like, instead of putting a NumPy array in a text file somewhere in a subfolder, we have the HDF5 files for the jobs, and then we can store the data in them much more efficiently, but still having the same kind of hierarchy of folders that is very appealing, I guess, for us as humans or as scientists to say, okay, where exactly do I expect to find the data? And we can then use this data, for example, here, I can extract all the volumes and all the energies, and then plot my first energy volume curve. All right, so the highlight, or what I want to highlight here is really the data management is all handled in the background, right? So really, again, that's something we don't want to teach our students what kind of file format to use, what's the most efficient format for a certain data set. This can already be automated, and that's good if we identify this once, and Pyiron is also flexible in a way. If there's sometimes a better format than HDF5, we were also happy to switch there, but at the moment, it's really like HDF5 offers us the most flexibility. And so it's implemented there, but the students don't have to look into this part. We can also then submit our calculations to the queuing system, right? So it's, I guess, the big challenge, or where I, in my personal part, or also for the study that I showed in the beginning, it's always easy if we just do a single for loop and submit calculations. Then we build loops on top of loops and interact with the queuing system. That's really where it gets complex. Again, in Pyiron, we try to make this as simple as possible, right? So you see here, the only thing that I had to add is which queue on my cluster do I want to submit to, how many calculations do I expect for each VASP calculation, and then I set a runtime limit, so how long do I expect these calculations to take. And if I want more information here, what Jörg already showed, right? So I can, on my server object, I can list the queues that are available on a given cluster. So those are the ones that are centrally defined. Then I can use those and choose from one and see how many cores I have available and so on. So here we really have a simple protocol. We have the Jupyter notebook controlling the calculation, and then they are submitted to the queuing system one by one. So that is already addressing a wide range of the high throughput project that we see, right? So just submitting individual calculations to the queuing system and then getting the results back and working with them. So Pyiron really interfaces with this and allows us as scientists, we never have to leave the Jupyter notebook environment. And so it's not that we just create all these calculations and then have to go into the command line and submit them and have this interruption there, but it's really all happening from the Jupyter notebook. We also have the built-in caching, right? So let's say you submit the calculation on one day, they finished overnight, now you go to the next day, you want to analyze your data or work with the data. Or by accident, maybe you execute the same notebook again. Pyiron will recognize these calculations already exist based on the folder structure that we have and the hierarchy there. And we just give you a warning message and say, okay, I found this calculation already, I'm just going to reload it. I'm not going to submit it to the queuing system again. Right, so if you have the same name, the same parameters, just says, okay, I think you don't want to run this again, you just want to reload it. So this kind of built-in cache also is very helpful, again, to save a lot of time rather than doing the calculations again or submitting them again by accident. Now coming to the later part of this loop, right? So how can we aggregate the data? I showed we can iterate over the jobs and just extract single quantities. What we would more typically do is we use a Pyiron table, and that's basically inspired by the MapReduce pattern. So we define functions, and each of these functions is going to be applied on all of our calculations. There are certain functions predefined. So here we, as I showed already, the get volume or get energy total. So that's also what Jörg showed this morning. And then we get our data frame and with these specific columns, right? So it's a very easy way to iterate over a huge number of data sets. And you can basically decide what are the properties I'm interested in. And we extract them from the HDF5 files and give you a pandas data frame with this specific data. The advantage of the pandas data frame here is we can directly put it into a machine learning framework and reuse it there, right? So it's very easy now to imagine, okay, we take this data, we couple it to a machine learning framework, get new information, maybe make a suggestion, what is the next calculation to do, run the next calculation, extend our data frame, and so on, and really continue this process to do a very large parameter study. In this example, again, I just use the data frame then to again plot my energy volume curve, just to show that it's consistent here. And so we really have this MapReduce pattern, which is maybe not so impressive for just 10 calculations. You can still do this with a shell script, and you go for hundreds or thousands of calculations. That's really where this MapReduce pattern really benefits us. And in the same way, as it's again a job, the table object is again a job object, so we can also submit this analysis to the queuing system and say, okay, this might take a bit longer, just submit it there, give me the data frame once you're done. The next layer of abstraction. We then found that, okay, we struggle at this point where we have more calculations or want to go to more fine-grained structure within the queuing system. Okay, then I have to hurry a bit. Yes, so here the structure is a bit more complex, right? So I have one notebook controlling the calculation, then I have my queuing system, and then I have for the different elements. So here I iterate over two elements, but you could imagine I do a study over the whole periodic table. For each element, I do multiple calculations, right? And that's where typically we already start to struggle. Okay, what is like a good way to do this? In this case here, we submit just the Merligan object, what we call like a parallel master object, and then this object can do the underlying calculations. And you see here, I specified 4 40 cores for my Monigan object, then 8 cores per VASP calculation. So the object will automatically decide, okay, I can run 5 calculations in parallel, and then another 5, and then the last one to again have the 11 strains. Also, the Monigan objects already provide certain predefined parts which are typically used. So in this case, getting the volume and energy. And so we can also, there's a built-in plot functionality. And we thought, okay, that's a very nice way, right? So it's handling the job management. It makes it much easier. We already have this predefined functionality. So that should be very helpful for our users. And that really comes now to the social part, where we found, okay, it's maybe not so easy, or it's easy to use these classes, but it's much more challenging than to develop new classes. So we found that only very expert users could implement new types of these classes and these kind of abstract functionality. And so then we looked back, okay, what were we doing before? Right, so before, typically we would have a shell script and have another shell script which is just changing variables in the script and iterating over the other script. So that's the same that we can also do in Pyiron, right? So we can write here our script. We have our input part where we say get external input. And we can then take the script and put it in what we call like a script job. So this again gives us more flexibility. So we can again have the same level of complexity of submitting one script job to the queuing system, running multiple VASP calculations inside, but have more flexibility in terms of like what's going to happen within these jobs, right? So you really have the ability to just create a Jupyter notebook, have your input in there, and then be able to modify this. And we also get the same results. So here just show the energy volume curves. So the script job is simple, extendable, but again, we were not so happy because it's breaking our system of having everything in one file and being able to connect it there. Oh, okay, sorry. The issue with the script job was that everybody has to implement their own task management. Right? So how many calculations to do in parallel, how many calculations run next to each other. That's where the part that the previous abstraction layer was often doing, but now the users have to do this again. So here we implemented the worker class, which again allows us, which basically acts as like a queuing system within the queuing system. So it really allows us to now manage the individual calculations and manage and distribute them within one larger allocation of the queuing system. So it was in particular when using larger systems like the nurse system, where only 2 of your jobs accrue wait time while they're in the queuing system. It's very helpful to have this kind of tools to really submit a larger allocation and then within this allocation distribute your workers. And so then we moved on and really tried to bring it all into one Jupyter notebook again. And so that's still more or less work in progress, but here I just show one prototype. We just say we define the different functions, and then we can assign this function to a new class and say, okay, which are the variables to iterate over? Right, so it's really just you define a function and integrate this template in there and then have a new job where you can iterate over these objects. We can apply the same Pyiron table and then finally have your energy volume curves. And then we said, okay, now we have the same flexibility. We have it all combined. That should be like the perfect solution for us. We started running more and more calculations. And then suddenly we got an email. There was a computing center and said, okay, look, please don't do this. Don't run srun. That was our lazy way of solving this. Instead of implementing a new work scheduler, we just used srun and created a huge amount of small tasks, and they weren't so happy about it. Obviously, that's slowing down the whole computing cluster if there's one person using srun to distribute the task within the allocation. So as part of the working group here, working on workflows, we're now looking into parts of replacing what we previously did with the Slurm part with the Flux framework, and I guess there's a talk on Friday also going into the details of the Flux framework, and that hopefully should address this challenge of us spamming the Slurm package, the Slurm queuing system there. I will skip the part of integrating new classes. So Pyiron is not limited to atomistic simulations. We try to make it easy to integrate new parts there. I will also skip the part about the melting points. Feel free to ask me about this. Maybe very briefly, one last challenge that we tried to address was really this part. Once you have the simulation protocol, how can we transfer the knowledge to other people? And it already starts with compiling the codes. Right? So like maybe one group is using one code and you're interested in trying this out, and then you look at the documentation and says, okay, 10 pages, 50 pages, it's not rare to find 50 pages to install the scientific code. And that's maybe the point where already a student would give up. So I spent a lot of time on creating, I guess by now, over 500 packages for the material science community as part of the Conda project. All they can be installed with a single line. Flux is one of these packages, so everybody who's interested in installing Flux, it's now available, I guess, starting last week. We have many more packages, and then by now, I guess we also achieved a point where new packages released in our community also appear on Conda Forge within, like, let's say, 3 months after they were released. Right? So it's really, the community starts to adopt this and starts to use it more and more to distribute the code. With this, we have different levels of abstraction. Right? Again, we have this high level user interface where users just provide individual parameters and don't care about what's happening on the scientific side. We have those users who are interested in the scientific steps. They can look into the Jupyter notebooks and see what exactly is done. We have Pyiron to handle the job management, data management, and the parsers. And finally, Conda Forge to do the scientific software management. Yeah, we also use this to publish our workflows, so that you find a publication template on our repositories where we combine the Jupyter notebook with additional resources like the classes, results, and parameter databases, and then publish this on the one end as like my binder environment so that users can interactively play around with this data, as well as like a small website to go through the different steps of a simulation protocol in a nice HTML document. If you're interested in this, for example, for the melting points, you find this as part of our GitHub organization. With this, I can come to the end. I do a little more advertising. So Ping Yang is going to give a talk on Friday as well, talking about how Pyiron can be used on the chemistry side. And I have many more different applications of Pyiron that are now also starting at Los Alamos. So Pete is, for example, from the MST division, using it as well to look at vacancy transport in disordered spinel phases. So again, ask him about his experience, right? So I'm very convinced about it because I developed Pyiron, but maybe it's also good to hear from people who are using it and maybe what are the shortcomings there. Yeah, I don't talk about the interactive part, and with this, I come to the conclusion. I hope I was able to show you that what motivates me to develop Pyiron is really this being application-driven, right? So like we start on the application, we think about, okay, what do we need to predict new material properties? What are maybe parameters that we haven't understood? Then we do parameter studies on those parameters to build the understanding there and maybe remove the human bias. And finally, all this is enabled by scientific software. I talked a lot about Pyiron, a little bit about the Conda Forge part or the FITSNAP project. And with this, I'd like to thank you for your attention.